Another thing that's going to be kind of an interesting or important aspect is how do we actually encode this type of movement? So if I'm going from state, A to state B, what's actually happening? So what we're going to do is we're going to zoom in on a couple of these to kind of see what that all looks like. So the first one is the situation where I have, again, farmer, wolf, goat, cabbage, where I have the goat on the right-hand side. And what's going to happen is I want to think about what actually happens when I bring the wolf across. So when I bring the wolf across, what's going to happen is that those two little cells, so the first two cells have to turn into ones because they're switching sides. So they're both going to uptick by a 1. So then I'm going to end up with this little vector. So I get 1, 1, 1, 0. What's officially happening there is I'm taking my starting vector, so the thing that has just the goat on the right-hand side, and I'm going to be adding this fancy little movement vector, which is going to tell me that the farmer and the wolf are the things that are moving. So if I merge those two things together, you can see that I do exactly get my 1, 1, 1, 0. So it's a really nice way that we can actually introduce movement, is that we're going to just uptick those two little cells and we're going to add a 1 to both of them. What ends up happening is that that exact same process works if I were to apply that exact same movement back again. So if I were to start, let's say, with the 1, 1, 1, 0, well, if I invoke the farmer is going to move the wolf, what's happening is that they're going to move from the right-hand side to the left-hand side. So they're going to go from side 1 back to side 0. So essentially, we're going to have to subtract a 1 because those two cells that were 1 and 1 now have to become 0, 0 because they're moving to the left. And we know that the other two things are unaffected. The cheap thing that we can actually do here is we can actually do addition, just like we normally did before, is that we can add this little vector of 1, 1, 0, 0. Because what ends up happening is that when I merge those two little things together, so if I took the little 1 and if I added a 1 to it, I end up getting a 2. But think that we're living in this nice little binary world, so there should be some type of reduction modulo 2 that's taking shape. So if I take that 2 and divide it by a 2 and record the remainder, it returns a 0. So I'm going to reduce that to modulo 2. And that's exactly how movement's actually going to happen, is that if I ever want to do a farmer and a wolf kind of direction, what I'm going to do is I'm just going to add this fancy little vector. It's going to tell me to change the position of the farmer and change the position of the wolf and keep the other two cells in check. And you can see that in general, that's all going to work very nicely. So you have, your general positions of things, and I've just identified them as A0, A1, A2, and A3. I can have a farmer and a wolf move. I can have a farmer and a goat move. I can have a farmer and a cabbage. So those are going to be embedded with slightly different little vectors. And technically, I could just have the farmer move as well. So again, he's going to just switch his sign. So his bit's going to flip. All of this is just bit flipping. That's all that's happening here, is that if I have a 1, it needs to switch back to a 0. If I was a 0 and I need to switch to a 1, I'm just going to add a 1. So it's always just this nice little addition in this kind of weird mod 2 setting. Technically, there's going to be other ways that we can do this a little bit more efficiently, but just kind of get the ball rolling, kind of not destroy everything quite yet. We're just going to be flipping some of these bits to indicate different types of movement. So it's kind of cute. It's pretty easy to do, and it makes for a nice little system. Again, be thinking in the back of your mind is that if I wanted to implement this thing, I would have to identify all of the possible states. Now I have all of the possible movement. And what I'm going to do is I'm going to make this giant little graph, and I'm going to try to identify a path that starts at the first one and then ends at the last stage and sneak them through, and then hooray, that's my solution to my fancy little riddle. So it's pretty cute and pretty tidy once you see it all kind of come into play. The last little thing of detail that one would need is just the identification of what are possible valid moves. So again, if I were to try to invoke a farmer and a wolf movement and they happen to not be on the same side, well, that should kick out some type of error. So if I were to begin with, 1, 1, 1, 0, and I wanted to move the farmer and the wolf, well, that works because the farmer and the wolf are on the same side. So that totally is valid. Whereas if I had that same starting state and I wanted to move the farmer and the cabbage, they're on opposite sides of the river. That should kick out some type of error. So the only time that movement should actually make sense is that if those two little cells are actually equal to each other. If they're both zeros, that means they're on side 0. If they're both 1, then they're on side 1. So we have this notion of what are some valid moves once we have this notion of kind of what the cells are all about. The last little thing that we need to chat about is then what would possible valid states be. So the idea is that certain states are valid, certain states are not going to be valid. And by not valid, I mean something's getting eaten. So the idea here is that basically we need to look at one of these, little collections, this little list of 4 objects, and identify where the farmer is, and then look at where the goat and the wolf are, and if they're together, then see if they're on the same side as the farmer, as well as look at the goat and the cabbage and see if they're on the same side as the farmer. If those differ, then something is going to actually be eaten. So the first one is going to see where the wolf actually eats the goat. So we're going to do a quick test to see if the farmer and wolf are apart. If they're not on the same side, then we ask if the wolf and goat are together. If that happens, then the wolf eats the goat, and we know that we're in a non-valid state. Same thing happens here. If the first cell, so the farmer and the goat, are not the same, so they're on opposite sides of the river, then we're going to ask, are the goat and the cabbage together? If that happens, then something's getting eaten as well. So again, this is just kind of a really quick, early, just getting your kind of brain tuned into the types of little systems that we're going to want to build up, and then a little bit of some of the checks that we need to have in play to kind of see what are valid moves, what are not valid moves, kind of getting that whole process all in play. And they're cute little riddles that are kind of fun. You take something that's really simple and really easy and then obviously blow it up into something that's far more complicated, but that has this nice generalization as we try to get more interesting systems, more interesting machines. All of these questions of computation come full circle.